Greetings and welcome to online lecture 4 on unit number 3, practical aspects of vapor compression system. This is the last segment of unit number 3, and in this segment we will discuss the balancing of vapor compression system. Vapor compression system mainly consists of 4 basic components, that is compressor, evaporator, condenser and expansion devices. These components have their own characteristics, which are the functions of evaporator and condenser temperatures. Generally, the system characteristics are obtained by superimposing the characteristics of these components. And mainly there are 2 approaches used, a graphical approach and analytical approach. Graphical approach gives the approximate results and convenient results up to when there is a superimposing of 2 to 3 components maximum. Like condensing unit, because there are only 2 components, that is condenser and compressor. But often the system may also include some ancillary components as well, such as cooling tower, boiler, ducting, etc. As the number of component increases, we can see there are more number of components. We can see that its pump is there, pump characteristics are also involved. Then heat exchangers, some intermediate heat exchangers are there. So if the number of component increases, an analytical approach provides the only feasible answer. However, the graphical solution gives a better visual appreciation and comprehension about the behavior of various components in the system. So today's lecture, we will mainly focus on only 2 compression or vapor compression systems. One is the condensing unit and other one a compressor-capillary unit. And only we are superimposing the 2 characteristics of the 2 devices. In the first case, in the condensing unit case, we'll mainly superimpose the characteristics of condenser and compressor. And in the compressor-capillary unit, we superimpose the characteristic of compressor and capillary tube. First of all, we'll discuss how to obtain the characteristics of condensing unit. Condensing unit, it mainly consists of compressor and condenser, and the performance characteristic of condensing unit is obtained by superimposing the characteristic of compressor and condenser, as shown in figure. We already discussed the characteristic curves of compressor in unit number 2. That is compressor, reciprocating compressor characteristic. Now, in this case, we are considering the chiller unit, that is, which mainly consists of shell and tube condenser, reciprocating compressor, and shell and tube evaporator. Now, here, for simplicity, we consider a reciprocating compressor running at a given speed. Superimpose those on the shell and tube condenser. This is the shell and tube condenser with inlet and mass flow rate of the cooling water is fixed. So considering this, these characteristic curves are developed, the combined characteristic curves. So here on the y-axis, we have a cooling capacity. On the x-axis, we have a evaporating temperature. Already we have discussed the compressor characteristic curves. So as the evaporating temperature increases for a particular condensing temperature, say 35 degrees Celsius, so continuously evaporating capacity or cooling capacity increases, and the rate is substantial, rate is exponential, and that is because of twofold effects, because as the evaporating temperature increases, mass flow rate increases, as well as refeeding effect increases. And the cooling capacity is the product of those 2. That's why the cooling capacity increases exponentially. So this is the effect of evaporating temperature on compressor cooling capacity. If we have to investigate the effect of condensing temperature for a particular evaporating temperature, suppose for at this particular point, as the condensing temperature increases, the cooling capacity decreases, and that is because of decreasing refeeding effect. Mass flow rate remains same, but this decrease is not that much substantial. There is small drop in refeeding capacity happens. So this is about the compressor characteristic curves, or the variation of compressor capacity with respect to evaporating temperature or condensing temperature. On the other hand, the condenser capacity, we will also see how the condenser capacity varies with the evaporating and condensing temperature. So first of all, we'll see how the condensing capacity varies with the evaporating temperature. Suppose if we consider a 35 degrees Celsius condensing temperature, so how the capacity varies. As the evaporating temperature increases, the condenser capacity, so the dotted line shows the condenser capacity. Condenser capacity increases gradually. There is a small increase of condenser capacity. And this increasing capacity is because of increasing mass flow rate. Because what will happen as the evaporating temperature increases, compressor pumps more amount of fluid through the condenser. So mass flow rate of refrigerant through the condenser increases. As the mass flow rate of refrigerant through condenser increases, its heat transfer increases due to increasing heat transfer coefficient. That's why the condenser cooling capacity also increases. This is one thing. Secondly, for a particular evaporating temperature, as the condensing temperature increases, the cooling capacity increases substantially. And this is because, suppose here the condensing capacity is 35 degrees, condensing temperature is 35 degrees Celsius for this evaporating temperature. With a fixed water inlet temperature. Water inlet temperature we are considering as suppose 30 degrees Celsius. So the delta T is 5 degrees Celsius here. So as the condensing temperature increases from 35 to 40 degrees Celsius for the same evaporating temperature, delta T also increases from 5 degrees Celsius to 10 degrees Celsius, then 10 to 15. So like that, as condensing temperature increases, the delta T across condenser increases. And due to that, the heat transfer rate increases and condensing capacity increases. So this way, the condenser capacity as well as compressor capacity varies with evaporating temperature and condensing temperature. Now, we superimpose these two characteristics, and the characteristic of condensing unit, that is A, B, C. This is a characteristic of condensing unit, and that is obtained by joining the point of intersection of characteristic corresponding to the same condensing temperatures for two components. Suppose A point where for the compressor case, condensing temperature is 35 degrees Celsius, condenser case also 35 degrees Celsius. B, both devices, condensing temperature is 40 degrees Celsius, and at C, both devices, condensing temperature is 45 degrees Celsius. Now, this is a characteristic of system, that is condensing unit. So, according to this characteristic, what it predicts. So, as the evaporating temperature changes, suppose as the evaporating temperature increases, the condensing temperature also increases. As the evaporating temperature decreases, the condensing temperature also decreases. Suppose this is a operating point B, and as the evaporating temperature decreases due to decreasing cooling capacity, suppose for example A, so the point A is reached, so the condensing temperature also decreases. So why condensing temperature decreases? Because as the evaporating temperature decreases, the load on condenser also decreases, and consequently there is a drop in condensing temperature. So condensing temperature also drops to 5 degrees Celsius, that is 40 to 35 degrees Celsius. And the same thing happens when the evaporating temperature increases. So this is the characteristic of condensing unit. So only one characteristic is not sufficient. So we have to superimpose the characteristic of all such devices, and by superimposing these characteristics, we can develop the characteristic of the systems. And we have to ensure that the system must work at the balance point. So this is the first segment, or this is the first case where we have superimposed the characteristic of compressor and condenser. Now the second case, that is we have to develop the performance characteristic of compressor and capillarity. Already we have discussed, these are the performance curves of compressor, as discussed earlier. As the evaporating temperature increases, your compressor cooling capacity increases, and as the condensing temperature increases, compressor cooling capacity decreases. So for three different condensing temperatures, we have obtained these curves. Now, as far as the capillary tube is concerned, if you see the capillary tube is mainly works on the pressure difference between condenser and evaporator. So larger the pressure difference, larger is the mass flow rate. Pressure difference lower, mass flow rate reduces. So mass flow rate varies with the pressure difference. in the capillary tube. Now we'll discuss the characteristic of capillary tube. So the dotted line shows the characteristic of capillary tube. Now, first of all, for a same condensing temperature, suppose 35 degrees Celsius condensing temperature, what will happen? As the evaporator pressure increases, the cooling capacity. Now, in this case, the mass flow rate is either cooling capacity or mass flow rate, because this curve its cooling capacity is again directly proportional to the mass flow rate. So for capillary tube, instead of cooling capacity, mass flow rate is applicable. As the evaporator pressure increases, what will happen? Mass flow rate decreases. And mass flow rate decreases because what will happen as the evaporator temperature increases, the difference between condenser pressure and evaporator pressure, that decreases. And because of decreasing the pressure difference, the mass flow rate decreases, and consequently cooling capacity also decreases. This is the effect of evaporator pressure or evaporating temperature. Now, on the other hand, if we consider for a particular evaporator pressure, if we change the condensing temperature, now what will happen? Suppose for this particular point, the point of operation. Now, for the same evaporator temperature or evaporator pressure, suppose if the condensing temperature increases, that is from 35 to 40 degrees Celsius. So what will happen? The mass flow rate increases, because as the condensing temperature increases, the pressure difference across the capillary tube increases, and consequently the mass flow rate increases. So in case of capillary tube, exactly reverse behavior is there. Capillary tube, as the pressure difference increases, definitely the mass flow rate increases or cooling capacity increases. So similarly, it gives a reverse characteristic as that of a compressor characteristic. Now, if we superimpose these two characteristics, that is compressor characteristic and condensing characteristics, thus the balance points are obtained. So these are the intersection points where the condition of both components are same. One point where compressor characteristic curves is that 35 degrees Celsius, and also condenser is also 35 degrees Celsius. Means at balance point, what it indicates, suppose this is the balance point. So at balance point, that is at the balance point, the compressor pumps out as much refrigerant from the evaporator as the expansion device feeds into it. Any unbalanced condition can only be temporary. Because this is the balance point. Suppose point number 2. Here the compressor mass flow rate is suppose this much, and the capillary tube mass flow rate is also same. So both mass flow rates are same. That's why it creates a balance condition. But under this, however, this compressor and capillary tube cannot fix the balance point independently. Because this is the balance point. This balance point doesn't depend upon only these characteristics of compressor and capillary tube. The evaporator heat transfer characteristics must also be satisfied. Because if they are not satisfied at the compressor capillary tube balance points, an unbalanced condition can result, and which may cause either starving or flooding of the evaporator. So that is very important, because compressor and capillary tube cannot fix the balance point independently. Here they are also associated with the evaporator characteristics. So evaporator should also support the behavior. So if the evaporator heat transfer characteristic changes, then unbalanced condition arises. And due to unbalanced conditions, there is a possibility of starving of refrigerant in the evaporator or flooding of refrigerant in the evaporator. Now that we'll discuss what is meant by starving and flooding. Now this is a figure shows the balance point of the compressor between the compressor and capillary tube. So suppose this is a compressor characteristic curve and a capillary characteristic curve, and this is a balance point. Okay. Now consider that load on the evaporator. Now load on the evaporator coil increases. Suppose due to increasing cooling capacity, now the load on the evaporator increases. As the load increases due to increasing evaporator capacity, the pressure also increases. So pressure increases from A to B. Now the new operation point, that is B. Now at this particular point B, now if we draw a vertical line, it intersects the capillary tube characteristic curve at MC, ME, and at compressor characteristic at MC. Now, what it indicates, so at this particular new operating point, that is point number B, the compressor draws more refrigerant out of evaporator than the capillary tube can feed into the evaporator. So less quantity of refrigerant come into the evaporator and more quantity of refrigerant goes out of the evaporator. So that creates a starving of refrigerant in the evaporator. Starving means there's a scarcity of refrigerant in the evaporator because more amount of refrigerant is going out of the evaporator and less amount of refrigerant coming into the evaporator through the capillary tube. Now this is unbalanced condition, but this unbalanced condition is temporary. What will happen? The correction process immediately starts. So what will happen in the correction process? Now here the compressor draws more amount of refrigerant. So more amount of refrigerant is entering into the condenser. So obviously because of that, the condensing temperature increases because more amount of refrigerant is going to the condenser. So it leads to increase the condensing temperature. As the condensing temperature increases, what will happen? Compressor mass flow rate increases. Okay, so this is a new mass flow rate of compressor. And at the same time, due to increase in condensing temperature, the compressor capacity decreases because this is in this direction as the condensing temperature increases for compressor case, and in this direction, condensing temperature increases for capillary tube. So the new balance condition will emerge. So this is a new balance condition. So whatever may be the unbalanced condition arises due to change in operating conditions, automatically the system arises to a new balance condition like this. So at this particular point, both deliver the same mass flow rate and the balance condition arises. So this is one case. On the other hand, consider now that if the load on the cooling coil decreases. So this is balance condition. As the load decreases, evaporating temperature decreases from A to C. So this is a new operating point where the evaporating temperature is decreased because of decreasing cooling load. And at this particular point, if you see, because if we draw a vertical line, it intersects the compressor characteristic curve at m dot C, and the mass flow rate corresponding to this is at this point, and capillary tube at this particular point. Now, what will happen in this particular case for lowering the evaporating temperature? What will happen? Compressor draws less amount of refrigerant, and while the evaporator feeds more amount of, or expansion device feeds more amount of refrigerant into it. Now, what will happen in this case? As more amount of refrigerant is entering into the evaporator and less amount of refrigerant is going out of the evaporator. So evaporator is flooded with refrigerant, liquid refrigerant. So this is a condition which generally arises. So it will therefore result in flooding. Eventually the liquid refrigerant may enter the compressor. There is a possibility because the evaporator is flooded with liquid refrigerant, and there is a possibility of that liquid enter into the compressor and can cause the damage. So in capillary tube systems, therefore, the refrigerant charge is carefully measured, and only that much refrigerant is charged as would just fill the evaporator. So adequate quantity of neither too high, neither too low refrigerant quantity is required. So adequate quantity of refrigerant should be charged in compressor capillary unit to avoid the compressor damage, because generally the compressor is in this particular case, whenever the capillary tube is used, in that case the compressor is of hermetical seal compressor. So in that case there is a possibility of flooding, that liquid may enter into the compressor if the load decreases. So now in this situation also, this is also a temporary situation. This situation, if we provide adequate quantity, now what will happen? Now in this case, what will happen? The refrigerant quantity goes to condenser is less. So obviously it reduces the condensing temperature. And as the condensing temperature reduces, the cooling capacity. So this is in this direction, condensing temperature reduces. So the new, so as the condensing temperature reduces, obviously the compressor start drawing more quantity of refrigerant. So mass flow rate of compressor increases here. At the same time of decreasing condensing temperature decreases the mass flow rate of expansion device. So the new balance condition arises. So this way, the balance condition arises after some time. So this is the beauty of compressor capillary unit. In this case, even though there is a change in operating parameter, like in this case we have discussed change in evaporating temperature, still the unbalanced condition arises, but that unbalanced condition is still temporary. After certain period, that again the balance condition emerges. So this is the way the compressor capillary tube system works, and this particular characteristic curves, it shows that the compressor and capillary tube it may cause starving if initially if the balance condition is shifted towards right, and it may cause flooding if the balance condition is shifted towards left. That will happen, but that is a temporary condition. That is called as a flooding and starving. Flooding means the refrigerant, the evaporator is flooded with liquid refrigerant, and starving means there is a scarcity of refrigerant in the evaporator. So these are the two important characteristic curves we have discussed. That is performance characteristic of condensing unit and performance characteristic of compressor capillary. So that's it. At the end of this particular topic, you should be able to explain how the performance curves of condensing unit and performance curves of compressor capillary tube are developed by superimposing the characteristic of individual components. And also, you should be able to give the answer what is mean by flooding and starving conditions in the capillary tube. With this, we have completed this unit number 3. So next lecture, we will start the second section, in fact, that is the air conditioning part with ventilation and infiltration. Thank you very much.